Will it work? Okay. So let me start. My name is Takuya Araki from NEC Japan. Today I'd like to talk about SX over Tsubasa and its application to machine learning. Okay, so NEC has released a new vector computer called SX over Tsubasa. It looks like GPU, but it has different characteristics. It supports normal programming languages like C, C++, Fortran, and provides better memory bandwidth compared to GPU. And vector computers have been used for HPC for a long time, but we want to extend it to AI machine learning area. So today in this talk, I will introduce SX over Tsubasa system and middleware implemented for machine learning. The middleware is written in C++ and MPI, and it provides similar API as Spark. In addition, we extended Spark to code middleware so that users can utilize vector hardware without being aware of it. Okay, here's the history of the vector computer. Actually, we have over 30 years experience for high sustained performance with vector computer. It started 1983, and around here, 2002, we provided a vector supercomputer called Earth Simulator. It was the world's fastest supercomputer in the world at the time. And the previous version of the vector supercomputer was SXS. And we provide new version of the vector supercomputer called SX over Tsubasa. Wait. So here's the product lineup of SX over Tsubasa. And actually, the product lineup includes from the small tower server model and rack mount server model to the supercomputer model. Until SXS, we only provided supercomputer model like this, but from SX over Tsubasa, we start providing a cheaper version of the server. So this is that's why we can we want to utilize the vector computer for areas like machine learning or AI other than HPC. And this can be realized by using the hardware called vector engine VE here. We implemented the vector processor as the PCIe card style. So here's the vector engine. It includes newly developed vector processor. And as I mentioned, it is PCIe card implementation. And it includes 8 cores. And the performance is 2.45 teraflops in the case of double precision. It's not that fast compared to GPU, but the memory bandwidth is very high, 1.2 terabyte per second. And it includes 48 gigabyte memory, which are also bigger than that of GPU. And in addition, we can utilize the normal program language like Fortran C, C++. So here's the specification of the hardware. The length of vector register is 256. So it is much larger than that of the Intel's AVX and such kind of SIMD vector interaction. And the number of core is 8, and the frequency is 1.6 gigahertz. And it also has the software controllable cache, 16 megabyte cache. And the 1.2 terabyte per second memory bandwidth and 48 gigabyte memory is implemented as HBM2 memory, and it has the 6 modules of the HBM2 memory. So here's the programming environment. We provide the vector cross compiler. It automatically vectorizes and automatically parallelizes the program. And we can utilize the latest version of Fortran C, C++, and also you can utilize the OpenMP and of course MPI. And you can just write the program on top of the Linux operating system. Actually, the hardware itself is PCI equals, so the host machine is just the normal Linux server. And you can write your program on Linux server and cross-compile the program using the cross-compiler. And then you can execute the created binary using the command like veexec. Then the veexec command sends the binary to the PCIe card, and the program is executed on the card. So it's quite easy. So here's the execution style difference from the GPGPU. And in the case of GPGPU, the main program starts from x86 side. And some computational extensive part is sent to GPGPU and together with data, and the result is sent back to the x86 side and so on. So in this case, we need a frequent PCI transmission, so PCIe becomes a bottleneck. And we need to use the special programming language like CUDA, and it makes programming a little bit difficult. But in our case, the program starts from the VE side, and only the system call is uploaded to the x86 side and executed on the host operating system. So in this case, we can avoid the PCIe communication bottleneck here, and we can use the standard program language like C++ Fortran. So why vector processor is faster than normal scalar processor? Because in the case of a vector processor, it can process many elements by one instruction, and that is supported by our large memory bandwidths. In the case of general purpose scalar processor, the data is loaded from memory one by one to the register, and the data is processed by scalar processing unit, and the data is stored to the memory one by one. And the memory bandwidth here is at most 0.1 to terabyte per second. But in the case of vector processor, we load the data from the memory by 256 elements at a time to the vector register, and the data is processed in parallel at a time using the vector register. And the result is stored to the memory again at a time. And that is supported by the large memory bandwidth, that is 1.2 terabyte per second. So you may think that this computation strategy a little bit similar to that of GPU. So the main difference, I think, from the GPU is that GPU is more computation performance oriented, but vector is more memory performance oriented compared to GPU. So GPU spend a lot of computation, a lot of transistor to computational circuits. But in the case of vector, we spend transistors for both data access circuits and computational circuits. So balanced size of computational circuits and data access circuits. So that is the, I think, the main difference from the GPU. And of course, GPU provides many small cores and requires special language. And in the case of vector, we provide only small number of large cores, and we can use general purpose, general programming language. So here I mapped the performance and the algorithm here. So x-axis shows the computation performance and y-axis shows memory performance. So here's general purpose CPU, and GPU is here, and vector is here. So, and we also mapped the algorithm of the machine learning here. And as you can see, actually deep learning, especially voice recognition, image recognition that utilize the CNN, these algorithms are actually computational oriented. So they are more suitable for GPU. But actually, other machine learning algorithms like statistical machine learning, say demand prediction, price prediction, recommender system, these kind of algorithms are more memory intensive. So we think these algorithms are more suitable for vector processor, and these are more suitable for GPU. And here in between, there are deep learning algorithms like much layer perceptron and LSTM. We think these are more or less between here and here. So we targeted accelerating memory intensive workload for HPC and AI. By the way, it seems here seems from the HPC context. Here is the kind of top 500 kind of workload, and here's HPC kind of workload. So in the case of machine learning, to support this kind of machine learning, we created middleware that speeds up statistical machine learning. So here's the middleware. Middleware that provides interface like Spark, and it is written in C++, and it internally uses MPI to implement distributed processing. However, users need not be aware of MPI to write distributed processing. Users just write functions in C++ and provide the functions to the middleware to run them in parallel. For example, if users want to double each element of a distributed variable, users just need to provide this function 2 times. Here, it takes I and returns I times 2. And here, D1 is distributed variable, and the user just needs to call member function map and give this function 2 times as the argument of map. Then the middleware calls this function in parallel and create new distributed vector here. So here's the full full sample program. And this program scatters a vector and double each element and then gather. So here's the initialization of the middleware. And first, we create the vector as the std vector and scatter the std vector using the make d vector scatter to create the new distributed vector here, d1. And this line is same as before. And you can gather the distributed vector using the gather member function. It creates this std vector. So as you can see, users do not have to be aware of MPI, that is SPMD programming style. It looks more like sequential program, and I think this is easier to write program compared to MPI. And here's, actually it works as an MPI program, and here in the constructor of this initialization, here this is the definition of a variable. In the constructor of the variable, MPI init is called, and then branches. In the case of rank 0, it returns from the constructor and executes the below statement. But in the case of rank 1 to n, wait for the RPC, remote procedure call request from rank 0 and never returns. And in this functions, rank 0 sends RPC request to rank 1 to n to do the work. And at the end of the main function, the destructor of this variable is called. And here, MPI finalize is called and send RPC, and the rank 0 send RPC request to rank 1 to n to stop the program. So here's the functionalities that is provided by the middleware. First one is basic functionalities for distributed processing, like map, reduce, filter, scatter, gather, sort, and so on. They are similar to Spark, and it's possible to utilize MPI directly. And we also provide matrix libraries for both sparse and dense matrix. And we also support matrix operations and linear algebra. And it is implemented by utilizing existing libraries like BLAST, LayPack, ScalePack, and RPack, and so on. And of course, we provide machine learning libraries, regression, logic regression, linear support vector machine with L1, L2 regularization, and ALS that is used for recommendation, and singular value decomposition, k-means, and so on. And however, writing C++ program is sometimes tedious, so we extended Spark to use as vector computer. So in this case, it calls the middleware through the same Spark API, and users do not have to be aware of the vector hardware. To implement this, we created a server with the functionalities explained before. The server receives RPC requests from Spark and execute machine learning algorithm and so on. But in this case, only previewed algorithm can be utilized from Spark. But anyway, it is very easier to utilize the functionality. And by this architecture, other languages can also be supported, and currently we supported Python. And to implement this, here, in the case of process request, rank 0 of the server waits for RPC request from the master of Spark. Here's Spark, and here's a server running on a vector engine. And the master do request to the rank 0 of the server. And as for data communication, all ranks or workers of the server and Spark send and receive data in parallel. So to make the data communication faster. And here's the implementation or the API. It provides same interface as the Spark's ML by changing. What we need to do is just changing the importing module. For example, in the case of original Spark program, here is the logic regression case. Here is the importing library. Here is the function call. And what we need to do is just change the importing module. And actually, we need to add some initialization and finalization. But the API for calling the machine learning algorithms is the same. Here's the preliminary evaluation. Y-axis shows the speed up compared to where the Spark is run. And here's the logistic regression. Here's K-means, and here's SVD. And blue bar shows the performance of Spark on x86. And red bar shows the performance on x86 with our middleware. And the green bar shows the performance of our middleware on vector engine overall. So we utilized Xeon Skylake latest one socket, and compared with the 1VE, the data is sparse one. The logic regression uses the CTL data provided by Criteria, and K-means and SVD use the Wikipedia document matrix. And in the case of, well, in most of the case, the performance on our middleware, performance of our middleware on x86 is much faster than Spark because we utilize the C++ and MPI for communication. And on vector engine, the performance becomes much faster compared to x86 and, of course, compared to Spark on x86. So conclusion, NC has released a new vector computer, SX or Tsubasa, and we implemented middleware for machine learning in C++ and MPI, and that runs on top of SX or Tsubasa. We extended Spark to utilize SX or Tsubasa with the middleware, and the evaluation results show that SX or Tsubasa is promising as a platform of high-performance machine learning. Thank you very much.
Maybe we can take one question.
I want to ask a question.
Yep.
So how many hardware threads do you support on the process?
Threads, hardware thread. Okay, so the physical core is 8, but well, there's no functionality like hyperthreading. Just the we only provide 8 physical cores. So you can run more than 8 threads on one socket, but it makes the performance, slower. So we recommend to just use that 8 threads on one socket.
So I know that for CPU, it supports double the number of threads than the cores, right? And it's hard for CPUs to fully utilize its memory bandwidth with data processing applications because of the it cannot, without enough hardware thread, it cannot.
Okay.
And for GPUs, it has thousands of cores.
Okay.
And thousands of more
Okay.
It can utilize the high memory bandwidth.
Okay.
And here you have a small number of
Okay.
threads and very large memory bandwidth.
Okay. So the question, in my understanding, the question is if we can't support many number of threads, how can we utilize the high memory bandwidth, right? So in that case, actually the size of vector register is very large, 256 elements. That means 256 times 8 bytes in the case of double precision. So it's very, very large. And for example, there's a machine instruction called vector load. Then vector load is issued, and then while waiting for the vector load, the processing unit can do other computation using the data on other vector register, right? So in our case, I mean, so the latency can be hidden by because vector register has enough size of data. Okay.
Right. So maybe we should conclude this session. And now, according to the schedule, we have a 30 minutes break. So people can relax. You can have some coffee. Yeah,
You were allowing us 30 minutes, or do we have to come back early to make up time?
all right. So we will come back at 10:30.
So the